In this video, we're going to look at the technique of integration by parts. It's a very handy technique when an integrand doesn't have a form that's easily integrable, and sometimes some things are just not integrated in any obvious form. And what we can do with integration by parts is break it down into simpler things, which then combinations of which can be integrated. It's a very, very handy technique, can deal with a lot of difficult problems. Okay, let's imagine we have some y as a function of x, okay, and we can write that function of x as two objects multiplied together. Okay, both are functions of x, u and v. U is a function of x, v is a function of x, and we can write the function we wish to integrate in the form of y equals uv. Now, by the product rule, we can differentiate that according to dy dx is v times du dx plus u times dv dx. And that allows us to work backwards to anti-differentiate things. So what we can do is rewrite this expression here, rewrite this equation, and put the second part, the last term here, to the front, and we can have dy dx minus v du dx. Okay, and then we can write that where it says y, we can replace with our original function u times v, u of x times v of x, which gives us y, so that dy dx is simply the derivative with respect to x, d dx, of the product uv. Remember, the product uv is just y. Now d dx uv minus v du dx is equal to u dv dx. Doesn't seem like it helps us much, but it will. When we start to anti-differentiate this, we have the integral u dv dx is the integral d dx of uv. Okay, now immediately that integral and that derivative, okay, will take us back to the original product uv. So that'll be handy. So there's a step forward already. And then minus the integral of v du dx. Now we can summarize that into a rule that's easier to remember, and that's the integral of u dv, bearing in mind that u and v are functions of x. So u dv is equal to uv minus the integral of v du. Now really it's u dv dx is equal to uv minus v du dx. We simply put it in that form because it helps us to remember it. Okay, just very handy that way. Let's have a look at an example to see its use. Now here's a function, x squared times e to the minus x. That's not immediately obvious how we anti-differentiate that. It's not immediately obvious at all. But with integration by parts here, okay, we can write it, we can break it down into things that are integrable. So let's have a go at letting u equals x squared. Then du dx is 2x, or du is 2x dx. Okay, and then that means that dv must be e to the minus x dx. Well, the antiderivative of that is v, because remember how we've got v du. So the antiderivative dv is v, the integral of dv is v, and the integral antiderivative right-hand side, e to the minus x, is simply minus e to the minus x. If you differentiate that, the negative will disappear and we'll be left with e to the minus x. Okay, so v, we've discovered now, is equal to minus e to the minus x. Well, that's very handy because that's helping us out a great deal, because now we've got u, now we've got v, and so the integral of u dv is uv minus the integral of v du. It's just in that form to remember. Remember, it's dv dx here, du dx. Okay, so let's write that out. U dv, so x squared times dv, which is e to the minus x dx, is equal to u times v, which we found to be x squared times negative e to the minus x. So we have minus x squared times e to the minus x, good, almost lost track of where I was, minus the integral of negative e to the minus x 2x dx, because if you remember that's v, which is minus e to the minus x, times du, and du we found to be 2x dx, so 2x dx. Okay, let's go down a bit further, and here we're left with minus x squared e to the minus x plus 2 times e to the minus x times x dx. Okay, still not, we've solved part of the problem, but we're still left with this bit here. Not sure what that could be, but that's all right. Just use this method again on the integral of x e to the minus x dx. So we let u equals x, okay? Du will be just dx. dv we let be e to the minus x. We don't have to worry about the 2, we've taken out front of the integral there. We'll just leave it there until the job is done. And so we have dv is e to the minus x dx, which we already know will give us v equals minus e to the minus x as an antiderivative. Okay, and so the integral x e to the minus x dx is u times v. Well, u is x and v is minus e to the minus x, so there we go. Minus the integral of minus e to the minus x dx, which we can anti-differentiate. That's very straightforward to anti-differentiate. We've already done that. We know that'll give us negative e to the minus x. The two negatives will cancel. This single negative out here will remain. And so this integral, x e to the minus x dx, will give us minus x e to the minus x minus e to the minus x. All right. Next step after that now is let's go back to the original problem. And that's the integral x squared e to the minus x dx is minus x squared e to the minus x plus, okay, 2 lots of this integral. So 2 lots of what we've just found above, which is just this one here. So all this bit here will come down, whoops, into here. So we have 2 lots of that, plus we have our constant of integration. Okay. And so expanding all that out, we have minus x squared e to the minus x, minus 2x e to the minus x, minus 2 e to the minus x plus our constant. Perhaps we can just factorize out minus e to the minus x, and we have x squared plus 2x plus 2 in parentheses, plus our constant of integration. And that is how something that didn't appear to be easily integrated has now been done so, simply by an application of this rule twice. Often you only need to apply the rule once, but if necessary, apply as many times as you need. Great technique. And a form to remember it in is, just coming back here, the form to remember it in is this one. Okay, that form there. Okay, the integral u dv is equal to uv minus the integral v du.